Hello class, welcome to our second section dealing with 1.4, which is collecting sample data. We're going to go through some more terms again. I know we've gone through a lot of different things over the past week or so, but this is the end of chapter 1 with all of these new terminologies because we're kind of starting from scratch with statistics because a lot of us haven't really done anything with statistics before, so we're going to be looking at those things again today. The first thing to look at is to look at designs of experiments. So remember, if there is an experiment, that means treatment was selected and chosen by whoever's doing the research. Otherwise, it's an observational study. So everything we're looking at today is dealing with experiments and selecting treatment and things of that nature. If it's not something like that, remember it's just observing, and that's a different realm of statistical analysis. A first good characteristic of a good experiment is randomization. Now, when we've talked about random sampling, okay, that's the number one thing to make sure of when it comes to good experiments. Subjects should be chosen into those groups at random. Now, some people say, well, what if by chance the one group is better than the other group? Well, that could be true, okay, but still, what other option do we have that would be better? Okay, if all of a sudden you start knowing things about the subjects and the data collection, it's no longer a random sample. Along with randomization, okay, what we want to do is have replication. Okay, so one sample typically is not good enough for that situation. So think of it this way. What if in my class I just had one big test and that was your grade for the whole semester? That would be a very challenging, difficult situation and may not show what everyone is capable of in a class. Instead of that, we have a randomized kind of set of questions, for example, on a test, and then we try to replicate that over and over and over again. Typically, larger samples allow us to notice things about different treatment effects and figure out kind of if it's working or if it's not working. Now, when we say large sample, it's not a specific number. So it's not like, if the number's at least 300, then it's good to go. If it's at least 1,000, it's good to go. There are some formulas to figure out what size sample would be good enough for a situation. And we'll look at some of those formulas as we move through the rest of the semester. If a large sample size is used, you still have to make sure it's a random sample. So for example, I don't want to just go ask 1,000 Purdue people what they think about Purdue if I'm trying to look at everyone in the state. Okay, just because I asked a lot of people, I could still get the same ineffective result because I did not do a random sample to collect the data. The next characteristic of a good experiment is what's known as blinding. So if you think about blinding, it's kind of covering your eyes or you can't see, things like that. Okay, a blinding experiment means the subject doesn't know if they got the treatment or not. Okay, so the idea would be I give one group a treatment, the other gets a placebo. Well, they don't know which one they got, so everyone thinks they got the treatment. This minimizes what's known as the placebo effect. If you've ever seen a young child, the placebo effect is real. For example, my kids will hurt their leg, and they'll say their leg hurts, and I say, okay, well, why don't we put a Band-Aid on it? And they say, okay, great, and then all of a sudden they feel better. That Band-Aid does nothing. Okay, they weren't bleeding or anything. They just have a bruise. That Band-Aid is not going to do anything, but that's the placebo effect, and we want to minimize that idea. So we blindly give everyone one of the two treatments, okay, or treatment or nothing, but they don't know that. Sometimes it's also good to have what's known as a double-blind experiment, where the subjects don't know what treatment they get, and the researcher doesn't. So I can't pinpoint and say, well, this is probably what's happening because you got the treatment and someone else didn't. You didn't get the treatment. I can observe and collect data about the experiment, and then I also don't know until the end. And so then hopefully between those two double-blind pieces, we can come up with a conclusion that would make sense. There's something experiments know as confounding. Now, confounding happens when in an experiment you come up with a result, but then there's some other factor that may have contributed to the result. Okay, so my example here says, I gave some of the subjects treatment, and the others did not get the treatment, but what I noticed is all the people that got the treatment were the women, and all the people that got the placebos were the men. And all of a sudden, well, our result says it's different, but medically, a lot of times studies are done on men and women because they react differently to different medicine or treatment. Okay, so there's something else going on here that we have to look at that may affect our final conclusion. Okay, ideally, a simple random sample would solve a lot of this, but you have to look at those things just in case to make sure, this is what's really happening in this scenario. The same thing could be true about tardies of my senior classes. Let's say all my senior classes are in the morning. I say my seniors are always late, and my junior high students are always on time. Well, it might be the fact of this first hour. Okay, so there's other things that could show up that make an experiment have confounding pieces in it. Okay, experimental designs. The best design is a completely random experiment. Okay, you assign the subjects and different test groups randomly using random selection, maybe a number system and random number generator, whatever it is. Okay, that would be a best case scenario. Oftentimes we have to do what's known as a randomized block design. So a block is where certain groups are similar. So the men and women idea with the experiment would be an example. Age range. Often at the doctor's office, age determines a lot of things. So once you hit a certain threshold, they start asking you certain types of questions, okay, about your health because you hit an age range or a situation. And so then those blocks are formed, and then groups from each block are dealt with and assigned treatment, and each block is looked at to see how they react. The next one is what's known as a rigorously controlled design. This is when researchers assign subjects with similar attributes and assign one the treatment and one not the treatment, or one the treatment and one the placebo. This is very difficult to do because there's one main group that this works really well with, and that would be identical twins. So the most recent version of that with identical twins was there was an astronaut that went to space for a long period of time, and then when he came back to Earth, they compared him with his identical twin and see how their properties were different from being in space versus being on Earth for an extended period of time. The problem is there aren't that many identical twins that are going to just readily be available to run an experiment. So instead, what typically happens is we do what's known as a matched pairs design, where you compare two treatment groups and they're paired up, and basically it's just yourself against yourself. The idea would be like if a doctor gave me a specific medicine, let's say I had high blood pressure. They give me a specific medicine to work to help with my high blood pressure. They observe and collect data for a certain amount of time. Then after a little bit, they say, all right, go off of that medicine, basically clean your system, and then go on a different medicine and see if it works better or not. So now I'm just comparing myself against myself. Okay, that idea is useful when it comes to the matched pairs design because I'm my best matchup. Okay, the same would be true about a car with different types of gasoline. Okay, and seeing which one gives you better miles per gallon. Use the same car. Now, granted, there's a little wear and tear. Okay, but you're using the same car to compare these two things and seeing which one's better. Okay, there are always going to be errors in experiments. Sampling error is going to happen. No matter how careful you are, there's going to be an error somewhere. Maybe you measure something a little bit off, or the way you collected the data. There's going to be more people that maybe fit a certain category than the other when you randomize it. Okay, the goal is if another random group goes through the experiment, we want our results to be close. Now, are they going to be perfectly the same? No. And if that were to happen, I would probably say, well, something's up here because there's no way two groups should be the same. For example, in a class that I have multiple sections, let's say I have 3 sections of this class, my goal would be that all 3 sections have about the same grade average. Now, it's not going to be perfectly the same. Maybe one group does a little bit better, one does a little bit worse. But on average, I should see that all 3 groups are doing about the same in the class. Now, maybe they're all doing really poorly, but at least they're all the same, which means I taught everything in a similar way. Okay, it's going to happen, okay, that the results are going to be a little bit different. But hopefully they're close enough that I'm satisfied with the results. Non-sampling error, which is the collection of it, or things like that, is the problem. So I had mentioned earlier about collecting the data. This is more of a non-sampling error. Okay, if I collect data and I measure something differently than what you measure it, okay, or you measure in inches, I measure in centimeters, okay, and things like that, the way that I collect and analyze the data, okay, may result in a biased result. This is a huge issue. We can control non-sampling error. Okay, so we can set everything up. Think of it kind of like the scientific method for statistics. We can get things set up in a way that makes sure everything is making sense statistically. However, when I go through the sampling, I'm going to have some type of error in my sampling method, or a sampling collection. Okay, it's going to happen. There's going to be some type of error. The next result's going to be different than the previous result. That's going to happen. I can't do anything about that. But what I can't have happen is the way that data is collected and things of that nature in order to have a problem with the sampling error. Make sure you're paying attention to all the different types of experimental design pieces. I know there's a lot of terms here. My suggestion is kind of as you're going through to have a little bit of notes. Not saying you have to have everything written out, but probably some notes would be good about each section in order to be useful on the test. Have a good day, everyone.